Welcome, curious minds, to another deep dive. Today, we're taking on one of the really big ones, one of the most mind-bending topics in physics, Einstein's theory of relativity. Our mission, if you will, is to sort of demystify it, help you grasp how space and time can actually bend, why clocks might tick differently near, say, a huge planet, how things might look shorter at extreme speeds, and maybe even touch on the possibility of time travel.
It's an absolutely incredible journey, really, into the fabric of reality itself. And we'll navigate it by understanding its two main pillars. There's the special theory of relativity and then the general theory of relativity. But to really appreciate these, we first need to get a handle on five sort of foundational concepts. We need to talk about space itself, the nature of light, gravity as Einstein came to see it, relative motion, and this thing kind of non-Euclidean geometry. So yeah, prepare to have your universe expanded a little.
Okay, so let's start with space. When we think about space, most of us probably picture, well, nothingness, right? Just empty room for things to exist in. But that's not quite right in the world of physics, is it?
No, not at all. And the profound insight here really is that space isn't just an empty void or some abstract idea. It's a physical entity. It has properties. You could think of it maybe like a pliable fabric or a dense sort of yielding jelly.
A physical jet. So if space is like this physical thing, what's the practical upshot? I mean, does it move? Can it change?
Absolutely. Yeah. Just like that jelly analogy. Space can contract and expand, and crucially, it can bend. So when space stretches or maybe compresses, the distances between objects sitting in that space change. And here's the kicker. If you imagine drawing what you think is a straight line on this jelly-like space, and then you bend the space itself, well, that line you drew will follow the bend. It will appear curved if you look at it from a different perspective.
Huh. That's a fascinating idea about space. And it brings us directly to non-Euclidean geometry, which sounds intimidating. We all learned Euclidean geometry in school, the geometry of flat surfaces, parallel lines never meet, at triangles, angles add up to 180 degrees, that sort of thing. But what if our surface isn't flat?
Right. This is exactly where Euclid's rules, they just don't apply anymore. If you imagine trying to do geometry on a curved surface like a sphere, a globe, well, many of those fundamental properties instantly break down. So for instance, on a sphere, you could draw two lines that start parallel, say, at the equator. But if you extend them long enough, maybe towards the pole, they will eventually meet. Or if you draw a triangle on a sphere, its internal angles will actually sum up to more than 180 degrees. And what we perceive as a straight line on that curved surface, the shortest path, will, from an outside flat perspective, look curved. That's a non-Euclidean geometry. It's basically the geometry of bent or rounded or curved spaces.
Okay, let's just recap quickly. So we've established space as this physical, bendable thing, kind of like jelly. It influences paths and distances. And we know that geometry itself changes on curved surfaces. Yeah. Keep those surprising facts in mind as we delve into how everything in the universe is constantly moving. All right, think about being on the road. A car passes you, going 40 kilometers. Simple enough. But what if you're also moving? Let's say you're driving towards that car at 30 kilometers. Well, then it appears to approach you much faster at 70 kilometers. Or if you're moving alongside at 30 kilometers in the same direction, it only seems to pull away slowly at 10 kilometers. So speed, it turns out, is entirely relative. Depends on your own motion.
Exactly. And if you zoom out for a moment, look at the bigger picture, the cosmos. Everything is in perpetual motion. Earth, the moon, the sun, distant galaxies, swirling nebulas, black holes. Everything's moving. And because of this constant cosmic dance, there's no fixed point. There's no such a thing as absolute motion or absolute rest. Everything is defined only in relation to, well, something else. And this leads us straight to Newton's bedrock laws of motion, his first law, right? An object stays at rest or moves at a constant velocity in a straight line unless some external force acts on it. This idea of uniform motion, or what physicists call inertial frames, is precisely where Einstein found some of his deepest insights.
Right, and that distinction between inertial and non-inertial frames of reference is really crucial here. So an inertial frame is where you're either at rest or moving at a constant velocity. You feel no net forces acting on you. It's like being on a super smooth train, moving at perfectly constant speed. Looking out the window, you almost can't tell if you're moving forward or if the world outside is moving backward.
Exactly. Conversely, a non-inertial frame is one that's accelerating, changing speed, changing direction. In that case, you feel the forces. You get pushed back into your seat when a car suddenly accelerates. Right. That means you can tell you're moving, or at least that your frame of reference is changing. This seemingly simple distinction, it really unlocks the core of Einstein's thinking about relativity.
Okay, now let's switch gears a bit and talk about light. Specifically, two really astonishing facts about it. First, the speed of light in a vacuum is an absolute constant. It's about 300,000 kilometers per second. And the amazing thing is, it never changes. It
Right.
doesn't matter where you are in the universe or how fast you happen to be moving relative to the light source. It's always the same speed.
Which just begs the question, right? How can light speed be constant? Unlike a car or a ball, whose speed definitely changes depending on how the observer is moving. Well, the remarkable thing about this comes from James Clerk Maxwell's equations. These equations describe light as an electromagnetic wave. And what they show is that light speed depends only on the unchanging properties of empty space itself, things like its permittivity and permeability. So that means its speed is universally fixed. It's baked into the fabric of the vacuum.
Wow. Okay, and the second mind-bending fact about light.
Nothing in the universe can move faster than light.
Nothing.
Nothing with mass, anyway. It's the ultimate speed limit. No matter how much energy you pump into an object, say a spaceship, you can get it closer and closer to the speed of light, but you will never actually reach it. It would take an infinite amount of energy, which is, well, impossible.
Okay, universal speed limit. Got it. Finally, let's talk gravity. Newton famously described it as this mysterious force that pulls objects together. But even Newton himself, he couldn't really explain why or how it worked that way, just that it did. And this raises several puzzling questions about gravity if you just think of it as a simple pulling force.
Yeah, you start poking at it and things get weird. For one thing, how is gravity different from other forces we know? Like the electromagnetic force or the nuclear forces, they have a limited range, you can shield against them. But gravity, its influence seems to extend infinitely, and you can't block it. And second, gravity is astonishingly weak. Think about it. A tiny little fridge magnet can easily lift a paper kite, defying the entire gravitational pull of the planet Earth.
Right, and here's another perplexing thing. How does gravity seem to know how hard to pull? It pulls heavier objects with more force and lighter objects with less force, but in just the right way so that they all accelerate downwards at the exact same rate. You know, the famous experiment, dropping a bowling ball and a feather on the moon where there's no air resistance? They hit at the same time.
Exactly. They hit the surface simultaneously. That just defies intuition if you think of gravity as a simple pulling force that just tugs on mass.
And this is where it gets really, really weird, and maybe the biggest problem for Newton's idea. His gravity seemed to act faster than light. Imagine if the sun just, poof, vanished right now. According to Newton, Earth would instantly feel the gravitational pull disappear and fly off into space. But we know light from the sun takes about 8 minutes and 30 seconds to reach us. So Newton's gravity implies an instantaneous action, which completely contradicts the universal speed limit that nothing, not even information about gravity, should move faster than light.
Right. And for centuries, scientists kind of conveniently sidelined these inconsistencies. I mean, Newton's formulas for gravity worked incredibly well for most things you could observe, like planets orbiting. But one scientist, he couldn't ignore them. Albert Einstein. He realized gravity probably couldn't be a force in the way Newton described it, and he set out to prove it, and in doing so, completely revolutionized physics with his theory of relativity.
Okay, wow. So let's put it all together. We now have this picture. Space is a physical, bendable thing, almost like jelly. Non-Euclidean geometry is what describes these curved surfaces. Everything in the universe is in relative motion, and we have these distinct ideas of inertial frames, constant velocity, and non-inertial frames, acceleration. We've also learned the speed of light is this absolute universal constant, the ultimate speed limit. And we've highlighted these really profound problems with Newton's description of gravity, strongly hinting that maybe it isn't a force at all. Okay, with these foundational ideas firmly established, I think we're ready to really plunge into Einstein's groundbreaking theory. Now, Einstein's path to relativity wasn't exactly straightforward. Apparently, he initially stumbled upon some prior work, rediscovered some things, actually, as did Max Planck around the same time. But then they each really blazed their own trails. Planck went on to lay the groundwork for quantum mechanics, and Einstein, well, he brought us the theory of relativity. We're actually going to start with general relativity, which deals with gravity.
And it all apparently springs from this legendary thought experiment that hit Einstein back in 1907. He was working in a patent office, of all places, and he observed, or maybe imagined, a worker falling from a roof along with his hammer and some tiles. And the key thing was, all three, the worker, the hammer, the tiles, they all fell at precisely the same rate.
Right. And from the worker's perspective, as he was falling, he, the hammer, and the tiles were all falling together. They appeared stationary relative to each other. He was just floating alongside them. Crucially, he experienced no jerk, no sensation of force acting on him, unlike, say, someone hitting the brakes hard in a car. This meant, in physics terms, that he was in an inertial frame of reference, even though he was falling. And the profound implication is this. If he was in an inertial frame, it meant no net force was acting on him. And critically, if no force was acting on him, then no force was acting due to gravity either. This led Einstein to this radical conclusion. Gravity simply isn't a force.
Okay, hold on. If gravity isn't a force pulling us down, then what is happening when we jump off something? What's actually going on?
This is where our everyday intuition gets completely flipped on its head. Einstein proposed that massive objects like our planet Earth don't pull things through space. Instead, they actually bend or warp the fabric of space around them. Think back to our jelly analogy. Earth puts a big dent in the jelly, so when you jump from a tower, you're not being pulled downwards by some invisible tether. Instead, you're simply following what is locally the straightest possible line through space that has been curved by Earth's mass. That bent path, that straight line in curved space, naturally guides you right back down to the ground.
Okay, but one might then wonder, if it's not a pull, why do things accelerate? Why do they speed up as they fall?
Ah, yes, acceleration. This is where the concept of space-time comes in. It's maybe Einstein's most brilliant synthesis. Space and time aren't separate things. They're intrinsically linked. They form a single four-dimensional fabric or continuum. Now remember, the speed of light, which is distance divided by time, has to be constant for everyone. So if space bends near a massive object, then time must also bend or distort proportionally to keep that speed of light constant. Time slows down where gravity is stronger. So gravity, in Einstein's revolutionary view, is the curvature or the bending of this four-dimensional space-time fabric, caused by the presence of mass and energy. Objects falling or accelerating towards a massive body are simply following the shortest, most natural path, what's called a geodesic, through this curved space-time. And it's the bending of time itself within this warped space-time that causes the observed acceleration. Things speed up because time is flowing differently along their path.
Wow. And this connects directly back to that non-Euclidean geometry we talked about earlier.
Precisely. Massive objects essentially distort the normally flat fabric of space-time into these non-Euclidean shapes. So when you fall from a tower, your path, which might seem like it should be parallel to the Earth's surface if you just kept going, inevitably meets the Earth because you're following a straight line through the curved geometry of space-time around the planet. Those parallel lines converge in curved space.
Okay, I think I'm starting to get it. Is there like a practical example we might know?
Well, a really dramatic, albeit fictional illustration is in the movie Interstellar. Remember when the astronauts land on that water planet near the giant black hole?
Yeah, time went crazy fast for everyone else.
Exactly. They spend maybe mere hours or even less on the planet where gravity, the space-time curvature, is immense due to the black hole. But when they get back to their ship, they find years have passed for the astronaut who stayed in orbit, where space-time was less curved. That's a cinematic exaggeration, of course, but it showcases the core idea.
Yeah.
Time slows down significantly in areas of extreme space-time curvature caused by massive objects. That's general relativity in action.
Okay, before we jump to special relativity, let's quickly touch on something called the equivalence principle. What's that about?
Right, the equivalence principle. It's actually a foundational idea for general relativity. It essentially states that, locally, the effects of gravity are indistinguishable from the effects of acceleration. Think back to Einstein's falling worker again. As he fell, freely, he felt weightless. He couldn't tell, just by his own sensations, if he was falling towards a stationary Earth in a gravitational field, or if he was maybe stationary in deep space, and the Earth was accelerating upwards towards him. To him, inside his little falling frame of reference, those two scenarios felt exactly equivalent. So essentially gravity, which we now understand as curved space-time, and acceleration, which is basically following a curved path through space-time, are, in a fundamental way, two sides of the same coin.
Got it. Okay, now for the other pillar, the special theory of relativity. You said this one applies specifically to inertial frames.
That's right. Special relativity deals with situations where there is no gravity and no acceleration involved. So it applies specifically to inertial frames observers who are either at rest or moving at a constant velocity relative to each other. And for special relativity, we have to keep two core postulates, two fundamental facts firmly in mind. First, the laws of physics are the same for all observers in uniform motion in inertial frames. Second, the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. That constant speed of light again.
Okay, the constant speed of light. That's where the weirdness comes in, right? Because here's the puzzle that arises. If you're on a moving train and you throw a ball forward, its speed relative to the ground is simply the sum of your throwing speed plus the train speed. That's just normal Newtonian physics. Makes sense. But
what if you shine the flashlight forward from that same moving train? According to Maxwell's equations, in Einstein's second postulate, the light speed relative to the ground will still be just sigma, the universal constant speed of light. It won't be sigma plus the train's speed. How? How is that even possible? It seems like a paradox.
It absolutely does seem like a paradox. And this is the very question that Einstein grappled with, leading him to another brilliant thought experiment. Let's imagine a spaceship. It's cruising through space at a very high but constant velocity, say 70% the speed of light relative to Earth. So it's in an inertial frame. Inside, an astronaut performs a simple experiment. They shine a laser beam straight up from the floor to a mirror on the ceiling, and then it reflects straight back down to a detector on the floor. Now, from the astronaut's viewpoint inside the spaceship, they are stationary relative to the experiment. The light beam travels a simple vertical path up and down. Let's say the distance to the ceiling is d. The light travels a total distance of 2d. The time taken would be distance over speed, so 2d divided by c. Simple.
Okay, makes sense for the astronaut inside. But what about us watching from Earth?
Right. Now imagine you are standing still on Earth watching this same spaceship whiz past through a giant window. Because the spaceship is moving sideways at high speed relative to you, from your perspective, the light beam doesn't just go straight up and down. By the time the light reaches the ceiling mirror, the spaceship has moved sideways. And by the time it gets back down to the detector, the ship has moved even further sideways. So for you, the observer on Earth, the light beam appears to take a longer diagonal path up at an angle than down at an angle, like a V shape stretched out.
Ah, okay. So the light travels a longer distance for the observer on Earth.
Exactly. It travels a longer path. But, and this is the absolute key, the core of special relativity, the speed of light must be the same constant c for both the astronaut inside the ship and for you watching from Earth. That's the second postulate.
Right. The speed is fixed.
So if the light travels a longer distance for you on Earth, but its speed must remain c, what's the only way for that to happen? Distance equals speed times time.
Time must also stretch out for the observer on Earth.
Precisely. For the math to work, for the speed of light to remain constant for everyone, time itself must pass more slowly for the astronaut inside the moving spaceship relative to your time on Earth. So you, watching from Earth, observe the astronaut's clock ticking slower than your own clock. This astonishing phenomenon is called time dilation. Moving clocks run slow relative to stationary ones, and it doesn't stop there. If time slows down for the moving observer relative to you, then for the speed of light distance time to remain constant, something else has to give. The distance, the length, must also change. Specifically, the length of the spaceship and the direction of its motion must appear to shrink or contract from your perspective on Earth. This is known as length contraction. So as you watch that fast spaceship zoom by, it appears shorter in the direction that it's traveling, and everything inside it seems to be happening in slow motion due to time dilation.
Whoa. Okay. Shorter and slower. But here's the kicker, right? And the true essence of special relativity. Because both you on Earth and the astronaut in the spaceship are in inertial frames, they're moving at constant velocity relative to each other, there's no acceleration involved. You can't actually say who is really moving and who is really stationary. Motion is relative.
Yeah.
So if you see the astronaut's clock running slow, what does the astronaut see when they look back at your clock on Earth?
They see exactly the same thing. From the astronaut's perspective, they are stationary, and you on Earth are the one moving rapidly past them in the opposite direction. So the astronaut observes your clock on Earth ticking slower than theirs, and they observe the Earth, and maybe your measuring stick, contracted in the direction of relative motion. That's the heart of it. Phenomena like time dilation and length contraction are relative. What you observe depends entirely on your frame of reference compared to what you're observing. There's no absolute time or absolute length.
Mind officially bent. Okay, so just to summarize quickly, special relativity applies to these inertial frames, constant velocity, no gravity, and it leads to time dilation. Moving clocks tick slower relative to stationary ones, and length contraction moving objects appear shorter in their direction of motion.
Exactly. And general relativity, the other theory, comes into play when gravity or acceleration is involved, dealing with non-inertial frames and the curvature of space-time.
Now, while these effects, time slowing down, lengths shrinking, they sound like something straight out of, I don't know, science fiction. You're saying they are actually real?
Oh, absolutely real, undeniably real. We just don't notice them in our everyday lives because the effects are incredibly tiny unless you're dealing with speeds very close to the speed of light, or in the case of general relativity, immensely strong gravitational fields. At the speeds we normally experience, the changes in time and length are practically infinitesimal, way too small to measure easily.
But we can observe them somehow.
Yes, we can, and we do. For instance, astronauts who spend extended periods in space, like on the International Space Station, are subject to both special relativistic effects due to their speed relative to Earth and general relativistic effects due to being in a slightly weaker gravitational field than on Earth's surface. When they return to Earth, they have aged slightly less than someone who stayed behind. The difference is measurable, though very small, tiny fractions of a second. They're measurably younger, biologically. And we see even more dramatic evidence in particle physics labs. Take particles called muons. They are created high in Earth's atmosphere by cosmic rays. When muons are at rest in the lab, they have a very short, known average lifespan, about 2.2 microseconds, barely any time at all. But the muons created in the upper atmosphere are traveling towards Earth at speeds very close to the speed of light, maybe 99% of c or even more. From our perspective on Earth, we observe these fast-moving muons lasting much longer, maybe around 11 microseconds on average, before they decay. That's a direct consequence of time dilation. Their internal clock is running slow relative to ours. Yet, crucially, from the muon's own perspective, its lifespan is still just that standard 2.2 microseconds. It's our observation of its time that's different.
Wow, that's compelling evidence. This brings us to a concept that often gets discussed and maybe misunderstood. The twin paradox. The classic setup is, imagine twin A stays on Earth. Well, twin B hops in a spaceship, travels out to a distant star at, say, 70% the speed of light, turns around and comes back. Let's say the journey takes 5 years according to twin B's clocks on the ship. When they reunite on Earth, the paradox claims twin B, the traveler, is definitively younger than twin A, the stay-at-home. Is that right? And why?
Yes, that's absolutely right. Twin B will be younger. But the common misconception is to try and explain this only using special relativity. People get tied in knots thinking, well, from B's perspective, A was moving, so shouldn't A be younger? That's where the paradox seems to arise. But here's the deeper truth and the resolution. The actual explanation lies primarily in general relativity, or at least in the fact that the situation isn't symmetrical like in pure special relativity. Why? Because the traveling twin, twin B, must undergo acceleration. They have to accelerate to reach that high speed. They have to decelerate to stop at the star, or just turn around, which is also acceleration, accelerate again to come back, and finally decelerate to land back on Earth. These periods of acceleration mean twin B spends significant time in a non-inertial frame. They feel forces. Their path through space-time is curved due to these accelerations. Twin A, on the other hand, largely remains on Earth, experiencing relatively constant gravity, essentially staying in a much flatter region of space-time, or at least a consistently curved one. It is this fundamental asymmetry, the fact that twin B experiences acceleration and travels through differently curved space-time, that breaks the symmetry of special relativity and leads to the real, measurable age difference. The traveling twin unambiguously ages less. It's not just relative, it's an absolute difference upon reunion.
Oh, so the acceleration is the key differentiator. It's not
Right.
just about the kind of velocity segments. Okay, that makes more sense. So we've untacked this incredible, intricate theory of relativity. It reshaped our understanding of space, time, gravity, everything. But this brings up a bigger question, doesn't it? Why is Albert Einstein so often hailed as, like, the greatest genius of all time? I mean, apparently his mathematical skills weren't even considered absolutely top tier for a theoretical physicist of his era. And as you mentioned, his theory doesn't even perfectly mesh with quantum mechanics, the other pillar of modern physics. So what made him so special?
That's a fantastic question, and you're right. It wasn't just about mathematical prowess, though he was certainly brilliant. A key insight, I think, is how he arrived at relativity. It wasn't primarily driven by analyzing existing experimental data or trying to explain weird results from labs, which is often how science progresses. No, the theory of relativity was largely born entirely within his mind. It was a product of his extraordinary creativity, his deep physical intuition, his ability to perform these powerful thought experiments we've discussed, and, well, what one might almost call a profound artistic sense about the harmony of the universe.
An artistic sense. That leads us to a broader discussion, maybe about the relationship between science and art.
Yeah.
Society often tends to put them in separate boxes, right? Scientists are the logical, analytical nerds, and artists are the intuitive, free-flowing creatives. You see it in movies, sometimes how teachers talk, maybe even how parents encourage kids. You're either a science type or an art type. This divide often seems quite ingrained.
It does seem ingrained, but if you look closer, if you bring this to a more universal scale, science and art are actually far more similar than they are different. They both involve observation, pattern recognition, creativity, imagination, and a quest for understanding or expression. And when you actually combine them, when you bridge that supposed divide, that's often where immense potential is unleashed. Think about modern examples like AI being used to generate music or visual art, or historical ones like the chemist Kekulé supposedly figuring out the ring structure of benzene after having a daydream about a snake biting its own tail. Really, the greatest achievements of humankind, whether it's the Mona Lisa or the Taj Mahal, or scientific leaps like Galileo's heliocentric model or Einstein's relativity, they almost always stem from this powerful blend of logical inquiry and creative insight.
So what's the takeaway from this regarding Einstein specifically? His genius wasn't just raw processing power, it was something else.
Exactly.
Yeah.
His genius seems to lie precisely in his unparalleled ability to blend the rigorous logic and systematic reasoning we associate with science, with the boundless creativity, intuition, and imaginative leaps we often associate with art. He could hold both perspectives simultaneously.
So one might then wonder, how did he do it? Was there something physically different about his brain?
Well, that's a fascinating angle. After Einstein's death, his brain was actually preserved and studied, although controversially. And researchers didn't find it was unusually large or anything like that, but they did find some interesting structural differences. Apparently, one key finding was that the connection between the two hemispheres of his brain, the corpus callosum, was remarkably thick and well-developed compared to average brains. The two hemispheres are typically associated with different types of thinking, the left more with logic, language, analysis, often dubbed the science side, and the right more with spatial awareness, intuition, creativity, the art side. So the theory goes, this enhanced connection might have allowed for an unprecedented flow of information, a richer dialogue, between his logical and his imaginative, intuitive processes. It might have physically enabled him to blend science and art in a uniquely powerful way, leading to the revolution that was relativity.
Wow. What an extraordinary deep dive that was. We've navigated the core concepts behind Einstein's theory of relativity, both special and general, and even explored what might have made Einstein himself such a singular, transformative genius. It's definitely a lot to take in, a lot to wrap your head around, so feel free to revisit any part of this deep dive whenever you wish.
Absolutely. This journey into space-time, into the true nature of gravity, and even into the workings of genius itself, it really illuminates the power of interconnected thinking, doesn't it? And how breakthroughs often emerge from bridging seemingly disparate ideas.
It really does. So thinking about all this, what stands out to you, our listener, about this interconnectedness? Maybe between fields you thought were separate, like science and art? And how might embracing both sides of your own brain, nurturing both your logical and your creative impulses, unlock new potentials or perspectives in your own life? Something to ponder. Keep exploring, keep questioning, and we'll see you next time for another deep dive.